In our last video, we found a crack in the armor, the single quote. We learned how a tiny character can break a database query. But a broken query is just noise. Today, we turn that noise into a weapon. Not all SQL injection attacks are the same. Some are loud and obvious, some are stealthy and slow. Understanding the difference is the key to both launching a successful attack and building an unbreakable defense. Welcome back to Vector Labs. All right, let's get started. SQL injection can be broken down into three main families, based on how the attacker gets information back from the server. These are in-band, inferential, or blind, and out-of-band. First up is in-band SQL injection. This is the classic, the most common, and the easiest to exploit. In-band simply means the attacker uses the same communication channel, the web application itself, to both launch the attack and get the results. The two most important types of in-band SQLi are error-based and union-based. Imagine an attacker sends a malicious query, and the website crashes, spitting out a detailed error message. That's error-based SQLi. The attacker's goal is to intentionally cause a database error that leaks information. These error messages can reveal database versions, table names, and even column data. From a defensive standpoint, this is why you should never show detailed, verbose error messages to users in a production environment. All an attacker needs is one revealing error to start mapping your entire database. Next is union-based SQLi. This is the real prize for an attacker. The union operator in SQL is used to combine the results of two select statements. An attacker exploits this by crafting a query that asks for legitimate data from one table, and then uses union to attach sensitive data from a different table, like the user's table, onto the end of the results. The application thinks it's just showing a list of, say, product names, but the attacker has secretly stitched the entire list of usernames and password hashes right below it. The defense here is strong input validation and parameterized queries. You have to treat all user input as untrusted. But what if the server is configured correctly and doesn't show any errors or directly return data? Then attackers move to blind SQLi. This is a much stealthier and slower technique. The attacker can't see the data directly. Instead, they have to infer it piece by asking the database a series of true or false questions. The first type is Boolean-based. The attacker sends a query like, does the admin username start with the letter A? If the page loads normally, a true result, the answer is yes. If the page returns an error or a user not found message, a false result, the answer is no. By asking thousands of these questions, an attacker can slowly, character by character, uncover passwords or other sensitive data. The second, even stealthier type is time-based. This is used when the web page looks exactly the same for both true and false results. Here, the attacker sends a query that says, if the admin username starts with the letter A, then wait for 5 seconds before responding. If the website responds instantly, the answer is false. If it takes 5 seconds to respond, the answer is true. This is incredibly slow, but for a patient attacker targeting a high-value system, it's a highly effective way to extract data completely undetected. So we've covered the loud attacks that show you the data and the stealthy blind attacks where you have to guess the data. But what if the server is so unstable that even a time-based attack is unreliable? That's when an attacker pulls out a rare but powerful technique, out-of-band SQL injection. Think of it like this. In-band is a direct conversation. Blind is tapping on a wall and listening for a yes or no. Out-of-band is when you slip the database a secret note, telling it to send the answer to a completely different address. The name out-of-band means the attacker uses a different network channel to get the data out. Instead of the results coming back through the web application, the attacker's payload commands the database server itself to make a network request, like a DNS or HTTP request, to a server the attacker controls. The payload might say something like, take the first letter of the admin's password and use it in a HTTP request to https://attacker.com/admin_first_letter. The attacker isn't watching the website for a response anymore. They're watching their own server logs, waiting for the answer to arrive completely outside of the target's web application. It's not very common because it requires these specific, powerful features to be enabled on the database. But for a locked-down, unstable server, it's an incredibly effective way to exfiltrate data. The defense here is a network security fundamental. Your database server should almost never be allowed to make outbound connections to the internet. By blocking that traffic at the firewall, you cut off this entire attack channel at the source. Fortunately, our local lab contains 3 different endpoints, one for each SQL injection type. We have /search_vulnerable, which contains an error-based and a union-based vulnerability. Then we have /search_victim_based for time-based injections, and finally /search_boolean_based for Boolean-based injections. As we've seen in the previous episode, if we send a single quote to /search_vulnerable, the server will crash, meaning that the application isn't handling our input correctly, and it's leaking database errors back to us. That's our first confirmed vulnerability. All right, next up is the /search_based endpoint. Now, what if the server doesn't give us an error? We need another way to get a signal. For this, we can use a time-based attack. We'll build a payload that asks a question and tells the database to sleep for a few seconds if the answer is true. Our question is the first letter of the blog page _admin user a B? Now, this app has a specific quirk where it'll sleep for 1 second for each row in the database. Since there are 7 users, we're expecting about a 7-second delay if we're right. Let's send a request and time it. And you can see the response took just over 7 seconds. That's our confirmation. We have a time-based blind vulnerability. Okay, last one, the /search_boolean_based endpoint. This one gives us a different kind of true/false signal. The application will respond with results found or no results. We can use this to our advantage. Let's ask the same question as before. Is the first letter of the blog page _admin user a B? If the server comes back with results found, that's our true condition. Let's send it, and we get results found. The application just confirmed our query was correct. So that's our third vulnerability, a Boolean-based blind injection. So we've successfully identified 3 different types of SQL injection vulnerabilities on this app. Now that we've confirmed they exist, we can move on to the next phase, exploitation. For that, we'll focus on the most straightforward one for exfiltrating data, the union-based injection we found earlier. Before we can pull any data out, we need to answer one crucial question. How many columns is the original, hidden query actually retrieving? See, for a union attack to work, our malicious select statement has to have the exact same number of columns as the application's original query. If we get it wrong, the database just throws an error. So, we need to find that magic number. My preferred way to do this is to just start building our union select statement piece by piece. We'll add columns one by one until the database stops complaining. We use null as a placeholder because it's a universal value that won't cause any data type errors, letting us focus only on the column count. Let's start by testing for one column. We'll inject union select null hashtag. The hashtag at the end comments out the rest of the original query. We send it, and we get an error. That's expected. It just means the original query has more than one column. No problem. Let's try 2 columns. We'll inject union select null hashtag. Send it, still an error. Okay, so we know it's not 2. Let's try 3. We'll inject union select null hashtag. We send that, and look at that. Still not working. Let's try 4. Still not working. So let's try 5. And hooray, our application loaded correctly, thus indicating that our current table has 5 columns. And we'll stop there for today. Let's do a quick recap. We went from pure theory to hands-on reconnaissance. We successfully identified error, time, and Boolean-based vulnerabilities, and most importantly, we found our magic number for the union attack, 5 columns. That step right there, finding the column count, is the key that unlocks the door. In the next video, we are kicking that door wide open. We'll take our 5-column structure, figure out exactly where we can inject our text, and start pulling out our first pieces of data, the database version, the current user, and more. The reconnaissance phase is over. The exfiltration phase is about to begin. You've made it this far, so you definitely don't want to miss that. Make sure you hit that subscribe button so you're ready for the next episode of Vector Labs. And I have a question for you. Which of the blind techniques, time-based or Boolean-based, do you think is stealthier? Let me know your thoughts in the comments below. Thanks for watching. This has been Access Point. I'll see you in the next one.